Welcome back. Let's talk quickly, well, I don't know how quickly it'll be, but about current, electrical current, and circuits. One of the things that we have to also get at is, well, what current depends on. There's an equation called Ohm's Law. In the reference table, they give it to you like this. I prefer to look at it like this, that says current, electrical current, depends on voltage and resistance. All right? The more voltage or potential difference you apply across, let's say, a resistor, the more current you get through the resistor. But the more resistance that resistor has, the less current you get. All right? So that's called Ohm's Law. All right? So current depends on voltage and resistance. All right? Resistance depends on these things, right? Here's a wire. It's got what we call a cross-sectional area. It's got a length, and it's made of something that has what we call a resistivity. That resistivity is listed for a few materials in the reference table. Okay, it's a property of each metal. So, you ought to be able to talk about what kinds of wires have more or less resistance. In general, more resistance, well, that's going to be longer, thinner. Some materials, like we said, have more resistivity than others, and therefore a wire made of them will have more resistance. And the other one is hotter. Notice we don't have anything about temperature in this equation because it's not a nice, easy algebraic relationship like it is for length and area. But you should know that the warmer a material gets, the more resistance it has. Okay? Okay, so that's that. Let's talk a little bit about circuits. So there's two kinds: series and parallel. All right. Here are some resistors connected to a battery in series. All right, R1, R2, R3, and we'll call that V total. All right, the process you're going to want to go through, or the things that you need to know, I should say, are that these three resistors have an equivalent resistance, or what we're saying is this circuit has a total resistance that you can find by adding each of those resistors. All right. What I would typically do first, if I can, is find that equivalent resistance. I would then use Ohm's law to find the total current in the circuit. Okay? And the big deal is once you find that total current, come here, that current is the same amount of current that goes through any one of these resistors. Whatever amount of current gets to here, well, it all has to go through this resistor and then comes out here, and then it all has to go through this resistor and comes out here, and all has to go through this one. And so, since there's only one path, the current in any part of that path is always the same exact amount of current. All right? And then, since assuming you know the current through each resistor and you know the resistance of each resistor, what you can do is apply what we call the loop rule and say that all of the voltage drops across each of those resistors have to add up to the total. All right? Classic blunder. Don't do this. Is the following example. All right? let's say there's a 120 volt source, and there's, I don't know, let's say a 60 ohm resistor, I don't know, a 40 ohm resistor, a 20 ohm resistor, and the question is, what's current in the 60 ohm resistor? Well, remember, classic blunder, don't do this. Why am I talking about it if I don't want you to do it? Because you'll do it, but hopefully you won't. People will say, okay, I want the current. Well, current is V over R. I see a voltage, that's 120 volts. There's a resistance, it's 60 ohms, so the current through that one must be, whoops, 2.0 amps. Well, that can't be. All right, there cannot be a 120 volt drop across that resistor. Because what about this resistor? What about this resistor? The voltage drops across those have to add up to 120. So no, no, no. Your first step is find REQ. You do that by adding these up. Well, it happens to be 120 ohms here. Then you'd say I total is V total over the total resistance. Well, that comes out to 1 amp. And then you say, okay, how much of the drop is across each one? Well, V20 is I20 R20. Well, that happens to be 20 volts. And V60 is I60 over R60. Notice, same current in each one. It's all 1 amp. Oops, so there's 60 volts. V40, I40, another 1 amp, times R40, and that's 40 volts. And oh yeah, those add up to 120 volts. Yay. Okay, so boo here, yay here. Okay, that's the big boo. Just because you see a voltage doesn't mean that's the drop across any one resistor. It can't be the drop over any one resistor. Okay? Okay, now the parallel circuits look like this. Let's say we have a V, and we got something like that. Okay? R1, R2, R3. Now, one of the big deals here is that since this, circuit has multiple loops that current can take, in this case 3 separate loops, a loop rule says that all of those voltage drops have to be the same. If this is 20 volts up, well, here's 20 volts down. 20 volts up, 20 volts down. 20 volts up, 20 volts down. Because in any loop of current, there's only one drop. Okay? The current, well, there's some amount of total current that gets to this place. Well, this is what's called a junction. All right? Some of the current goes one way, some of the current goes the other way. And so the total current has to add up to the current that runs through each branch. Current is electrons. Right? If 1,000,000 electrons get to this point and 200,000 of them go this way, well, 800,000 of them go this way. If of those 800,000, 200,000 go this way, well, the other 600,000 go this way. All right? So you literally have to add up those currents. Resistance works a little bit oddly, as you, I'm sure, remember. 1 over REQ is 1 over R1 plus 1 over R2 plus 1 over R3. And I'll just remind you that adding fractions involves finding a common denominator. Okay? And also remember that when you do this, you add up those fractions, that doesn't get you the equivalent resistance. That gets you 1 over the equivalent resistance. Don't forget to flip. Don't forget to flip your final answer. Okay? So, let's see. What did I just want to say? Yeah, the one thing I wanted to, that's worth mentioning is that over here, for series, adding a additional resistors makes REQ get bigger. Over here, adding additional resistors makes REQ get smaller. All right, not a bad thing to have in the back of your mind. Here, we add an additional resistor, but we're just adding another path that current can take, and therefore that drops total resistance. Here, adding another resistor just puts another constriction in the one single line, and that makes total resistance get bigger. Okay? Other things, electrical power. I'll say an energy. Three equations define electrical power. All right, so yeah, it can be maybe a little tricky to know when to use each one, but I guess do your best. What I look for these is if there are questions about power and say, maybe different resistors in the same circuit. Well, for series circuits, well, current's always the same, right? All right, so if current's the same, then let's not worry about that. More resistance means more power, right? So if I is constant, like in a series, a bigger resistor uses more power. But like in this one, if V is constant, like in, whoops, I spelled that wrong. Like in a parallel circuit, that means that if there's more resistance, that uses less power. So that can be a little tricky, but what you got to do is look for what kind of circuit they're talking about. And if you can make one of these quantities, I or V, constant, then you can find a relationship between power and resistance. Okay? And then the other thing with electrical energy, the deal is, power by definition is the rate at which work is done, or a conversion of energy per unit time. So energy is power times time. So you'll see equations that energy is power. Well, that could be I times V times T. Or power V squared over R times T. Or power I squared R, times T. All right, so questions about how much energy a light bulb uses or something like that, you're going to typically use one equation to find the power and then multiply by the time in seconds. Okay? All right, there's your electricity and circuits and current overview.